Welcome to our first lecture on geology, earth science. So earth science, geology, is where we are going to take what we've already learned about physics, what we've already learned about chemistry, and now apply that information to studying the earth. And of course, the cover of our textbook is something that deals very much in earth science. We have a picture of a rock outcropping here with some material that has been eroded away. So let's just get right into this. We're studying geology. And first things first, we've just finished chemistry. And the geosphere is the entire Earth. It's a spherical shape, so geosphere is made up of rocks and minerals. That's what our Earth is made of. But of all of those elements in the periodic table, and by the way, here is the periodic table as you'll see it on the test, or you may have already seen it on the test by the time you view this. So of all of those elements, all of the elements on the periodic table, 98%, whoops, that's the wrong tool, 98% of the Earth's mass is made up of just 8 elements. And so here are our primary elements: iron. 1/3 of the entire mass of the Earth we believe to be iron. Oxygen just behind, almost 1/3, is oxygen. In fact, you combine these two, iron and oxygen, you're over 60% of the Earth is just those two, iron and oxygen. Then 15.6% silicon, 13.9% magnesium. So there we have 4 elements. 4 elements form the vast majority of the mass of the Earth. And then the rest of the ones that are shown here, now remember, it was only going to 98%, so it was counting out sodium and all the rest. You have nickel, calcium, aluminum make up the last common elements, if you will, in the Earth. Now you read that and you're like, well, what about other things? We have, like, chlorine's not listed there. Sodium chloride isn't salt, really plentiful? Yes, it is. But in terms of the total Earth, it's a small component. Now, if we look at the geosphere, if we look at the entire Earth, one thing we need to do is to understand what the Earth looks like. So we know that the Earth is a sphere. I know there are those people out there who try to say it's flat. They are pretty much ignoring every possible scientific experiment that can be done and just closing their eyes. So the Earth is a sphere, and if we start at the surface, that's where we are. So we live on the crust. The outer portion is the crust. And if you look here, it lists 2 types of crust here: oceanic crust and continental crust. The oceanic crust is under the oceans, and you see that it's thinner there. So it says here about 5 kilometers. The continental crust, where we live on land, is thicker, 30 to 40 kilometers. What's the difference? It comes down to composition. The oceanic crust is a more dense and thinner material. The continental crust is a less dense and thus thicker material to have the same weight. The crust is the only part of the Earth that we as humans have ever explored. No one has ever drilled through the crust into what's listed here as the upper mantle. Everything under that is based on interpreting measurements of what we see going on the Earth. And we'll talk more about that later. So right now, we're giving you what we believe is in there. Later on, how we get that information. Now, the radius of the Earth here, 6,371 kilometers is the radius of the Earth. Of that, it's a very small fraction that is the crust. Underneath the crust, we have the mantle. Now, the mantle is this entire region. All of that is mantle. So if you see right here, the entire mantle is about 2,885 kilometers thick, but it's broken up into 2 pieces: the lower mantle and the upper mantle. The upper mantle and lower mantle are fundamentally different in how they behave. And you have this here, it says the asthenosphere. The asthenosphere is the region where the temperature and pressure are just right so that the soil, or the whatever you want to call it, it kind of can be deformed. And so the upper portions, the things that are above the asthenosphere, which is not listed here, but we call that the lithosphere. So what's above the asthenosphere is the lithosphere, and it contains part of the upper mantle and the upper mantle and the oceanic crust. That's what makes our tectonic plates, the pieces on the surface of the earth that slide around. So we have the upper mantle, the lower mantle, and then under the mantle we have the outer core. This outer core is liquid. So it's molten rock, what we call magma. Magma is the name for the molten rock. Now, you probably are already saying, wait, I know a little bit. And if I go to a volcano, we have lava. Well, what's the difference in lava and magma? Once it gets to the surface, we call it lava. When it's below the surface, we call it magma. So lava is also molten rock, but it's molten rock that's reached the surface. So this is a large magma chamber here that's the outer core. And then the inner core is frozen. Now, when I say frozen, you think cold because, of course, ice is frozen. But you know what? You take a piece of rock that is frozen as well. It's frozen because it has solidified into a solid form. You could heat it up and melt it, and then it would be liquid. Heat up some more, and it would vaporize. So frozen doesn't mean cold. And in fact, it's super hot there in the inner core, but the pressure is so high that it forces it to form a solid. So that solid inner core is the center part of the earth. So we have the inner core, the outer core, the mantle, the lower and upper mantle, and then the crust. So that's the composition of the earth. And just as you might expect, you know that if you have water and you throw a rock on it, the rock sinks. And we did a lab on this. We know that the rock sinks because it's more dense. Well, the same happens with the earth. You have things like iron that are pretty dense, things like silicon dioxide, what we call silicate, that is not very dense. So that silicate floats on iron. And so what we have is the more dense things have sunk to the center of the earth. So we believe that the stuff in the inner and outer core is primarily iron with nickel, because that's the most dense of the common material that the earth is made of. And so the lighter elements float to the surface. So we have silicon and oxygen-rich materials that have floated to the surface. So if we look at just the crust, now the crust is the part that we can actually probe. The crust is 46.6% oxygen, almost half oxygen, and 27.7% silicon. That's a little more than a quarter silicon. So silicon and oxygen together are 75% of the Earth's crust. And then we have aluminum, iron, calcium, sodium, and the list goes down, that make up the rest, the last quarter of the Earth, of the crust of the Earth. So is aluminum plentiful? Well, it's a lot more plentiful than iron in the crust. So one would have to say aluminum is fairly plentiful. To be honest, though, extracting aluminum is fairly expensive. Now, we have some words here that you use a lot, but you probably don't have a good feeling for. And minerals is the first one. Minerals are, number one, naturally occurring, and number two, crystalline solids. Now, if it's crystalline, that means that you have atoms in a fixed pattern. So here's an example of a fixed pattern. Atoms that are in a fixed pattern as you go through it. So the minerals, they're naturally occurring, they're not man-made, not manufactured, and they're crystalline form. And these minerals have specific chemical compositions. So we've learned, for instance, about sodium chloride. Don't know why the L didn't work out right. Sodium chloride, that is a crystal with sodium and chlorine atoms, and it occurs naturally. It has a crystalline form. It's a mineral. They're generally inorganic. Remember, organic means carbon-based, so inorganic, generally not carbon-based. But there are some minerals that are carbon-based. Now, we classify minerals by both their chemical composition and their crystal structure. Chemical composition alone isn't enough to identify some minerals. And so, I'll show you an example coming up. So the crystalline structure is also an important thing. The crystalline structure is talking about the geometric arrangement of atoms in the crystal. So the types of things that we actually will sit down and try to classify something with is the crystal form, the shape that the crystals take on. Hardness is, well, I mean, it's hard, but let's just be honest about that. Cleavage and fracture. Cleavage is if you hit it, it fractures or it breaks on certain surfaces. So if you look, for instance, at this picture of the quartz has a certain cleavage plane where it naturally fractured. Well, see, I say fracture, and I need to keep those words separate. Has certain planes where it cleaves. In this pyrite, it's very clear that there are certain planes there. Whereas if something fractures, it doesn't form a nice, even, flat surface. It just is all over the place. Then we have the color. Well, color is pretty clear. Density, we state density fairly enough. So that's something that you can figure out well. Now, I want to look at these pictures just a little more because I don't think I talk about all of them in slides coming up. This here is what we call the streak. When you measure streak, what you do is you rub the rock on a streak plate, a piece of porcelain, and you look at the color it leaves behind. If you look at this here is, it looks like a black rock, right? It's hematite, it tells us. But when you rub it on that porcelain plate, it gives you a reddish brown color. So that's the streak of hematite. And so one of the things that a rock hound will do, they'll get this rock and they will scratch it on their little streak plate to see what color the streak is. These here, you notice they're both feldspars, which is German for a field rock. Plagioclase versus potassium, very different in color. So they're both feldspars, but they are very different. Another one that I don't think I talk about is how you determine if something has calcite. If you put an acid on it, it will react with the acid and bubble. This is exactly what we did in our lab with mystery powders. One of our tests was to put the hydrochloric acid in there and see if it reacted. And if it did, then we knew it was a carbonate. So calcite is calcium carbonate. So that's another test. So you have two rocks that look just the same when you find them, but one's calcite and one is quartz. You put the hydrochloric acid on the calcite, it bubbles. You put it on the quartz, no reaction. And it's easy to differentiate that test. So a good geologist always carries around a little container of hydrochloric acid so they can make that test. And they carry around a streak plate so they can make that test. This doesn't have any of the other tests here, so I'm not going to go into the other things. Well, I will say, as a good geologist, you have other things. You want to have something for scale. You might see lots of pictures where people will put like a hammer in the picture. The reason they put the rock hammer in the picture is so they have a sense of scale. Or they might put a nickel in the picture, so you have a sense of scale. Or some people are better and they have actually something that has markings on it. So you actually have a measured scale there. So that's another important thing. Also, things that are hard that you can try to scratch them with to test the hardness. So let's look at these properties a little more carefully. So crystallization is the process of forming a crystal, growing a crystal. And you can grow from liquid or gas. When I was doing my research in graduate school, I worked with sapphire. And sapphire is a crystal that is grown in an aqueous solution, in a water solution. The atoms form very specific chemical compositions and geometric arrangements. And so many minerals are identified by their crystal form, by the shape they take. The internal arrangement of atoms is what determines the shape. And you can actually, with the same chemical composition, get a different crystalline form depending on the temperature, pressure, and how much room you have where it's made. So if we compare minerals, these are all the same chemical composition. They're all elemental carbon. You have diamond and graphite. What's the difference in diamond and graphite? It's the crystalline structure. This diamond structure is very complex, very complex. And to get it to form that structure, it has to be formed under very high pressure. Graphite is a unique situation where you have planes of hexagonal rings and one plane above the other. The bonds between those planes are very, very weak. So graphite's very easy to peel off or flake off layers. And of course, you would never get confused looking at the two. The diamond looks very different. So the conditions under which they were made are very important to the properties. Now, hardness is a measurement of how hard it is to damage the surface. So something that's hard, it's difficult to damage the surface. And we have this thing we call the Mohs hardness scale. And the hardest thing is diamond. Diamond has a hardness of 10. Corundum. Corundum is the same thing as sapphire. There is a technical difference, but they're chemically the same thing. So I did my research. Sometimes I call it corundum, sometimes I call it sapphire. So corundum sapphire is also very hard. Then you have, topaz is 8, quartz is a 7, orthoclase, which isn't going to be anything to you, 6, apatite 5, fluorite 4, calcite 3. So calcite is a very soft rock. So another test to differentiate calcite from quartz would be how hard it is. Then gypsum, very soft, talc, very, very soft. Your fingernail is about a 2.5. So if you can scratch a rock, it's lower than 2. If you can take your fingernail and scratch a rock, then its hardness is less than 2.5. If you try to scratch your fingernail and you can't, then it's harder than 2.5. A copper penny is about 3.5. So if you could scratch it with a copper penny, then it's softer than 3.5. So that, you could say, oh, is this calcite or quartz? Let me take out my penny and see if I can scratch it. If I can scratch it, it's calcite. If I can't, it's quartz. A typical knife blade is around 5.5, steel nail 6.5, masonry drill bit, those are hardened, 8.5. So you can determine the relative hardness with these simple things. So these are things that a good geologist might have in her backpack as she's walking out there so she can test these things. So it's called the Mohs hardness test. 10 is the hardest and diamond is 10. You don't have to know all these ones in the middle. Talc is the softest one on this, is a 1. So talc is very soft, diamond is very hard. I already talked about the difference between cleavage and fracture. So an example here, you have a piece of muscovite, and if you put your little razor blade on there and you tap it, you get these fine, nice flat sheets that will break in. Feldspar is not so flat because it has 2 cleavage planes that are perpendicular to each other. But then you have this step type structure that you form. Now, if you go to the halite, halite is rock salt, sodium chloride. It's it has 3 cleavage planes now. And so it forms these, not cubes, but cuboidal shapes. And then the final example here is calcite. Calcite has 3 cleavage planes, but notice they're not perpendicular like they were with halite. And so it forms these prismatic shapes. And those aren't the only options. So here we have an example of fluorite, which has an octahedral crystal and breaks along 4 cleavage planes. So you can see the cleavage tells you a lot about the crystal. And if it won't cleave, then it fractures instead. Minerals that fracture don't exhibit cleavage. They just break however you break them. Now, color is a very obvious distinction, but it's not really as useful as it seems because just a little impurity will change the color completely. So everything on this page is fundamentally Al2O3. This is what sapphire looks like if it's pure. That's pure sapphire. It's just a clear glass. What you think of as the gemstone sapphire looks blue. Why does it look blue? It has impurities. Ruby is a sapphire with chromium impurities. And you have different colors of sapphires depending on what impurities are present. So a pure sapphire is going to be perfectly transparent. A deep blue one, and I can't remember what the impurity is. I should have looked it up before class. But it has impurities to give it that blue color, different impurities to give them the other colors that are possible. So the first of your clicker questions, which of course you're not going to use a clicker for. The physical properties of a mineral are predominantly related to what aspect? Is it the external conditions of temperature, pressure, and mass space available for growth? Well, that was one of the things that I said. I said that with the carbon, for instance, different conditions, if you have a high pressure, high temperature situation, you can form diamond. But if you don't, you form other things like graphite. The chemical composition and internal arrangement of the atoms that make up the mineral, absolutely. Different chemical compositions are going to be different minerals, and they're going to have different cleavage and so on. Crystal form, hardness, cleavage, fraction, density, that's how we identify them. So I'm going to go with all of the above because now we're talking about slightly different things. This is how we identify. These two here are very closely related with how they form. But all of those are very important to mineral identification. Now, rock-forming minerals, we break down into 2 general classifications. Silicate minerals. Silicate means it has a silicon dioxide basis. And non-silicates. Silicate minerals are 90% of the Earth's crust. Now remember, the Earth's crust was about 50% oxygen and about 25% silicon. It was actually 27 and 47-ish. But if we note here, silicon dioxide, you have one of these for every 2 of those. That makes very, very good sense that those are the 2 dominant elements in the crust if the minerals in the crust are 90% silicate. Now, silicate minerals are made up of silicon and oxygen, as I said, silicon dioxide, as well as some other, shall we call them contaminants, other elements. And so here is the base of the silicate rocks. It's a tetrahedron that has the silicon here and oxygens all around. Now, of course, you guys you can count, and you recognize this has 1 silicon and 4 oxygens, right? Sorry, I sneezed. That is the base of the silicate rocks. But when you put these together, your next oxygen is going to share the 3 corners So these three corners are going to be shared with the next, or silicon, excuse me, the next silicon on this side, and likewise all around. So on average, when you're all done, it averages out to one silicon and two oxygens for the rock. Now, among silicate minerals, we subdivide into ferromagnesian. Ferro means iron, magnesium means magnesium. So these are rocks that have iron and or magnesium. They tend to have a high density because iron and magnesium have high densities, and are darkly colored because of iron and magnesium. And then the other silicate rocks are non-ferromagnesian. That's anything that doesn't have iron or magnesium. And they tend to have a low density and are light in color. So if it's light in color, it's more likely to be non-ferromagnesian. If it's dark, it's more likely to be ferromagnesian. Feldspar, German for field rock, is a silicate rock family that makes up about 50% of the Earth's crust. So 90% is silicate, and of that 90%, over half of it is feldspars. So feldspars are just common as the sun. And feldspars have lots of different variations. In fact, you saw earlier where we had a potassium feldspar and a plagioclase feldspar, and they looked quite different. Now, the 8% of the crust that is non-silicate contains a number of different things, carbonate minerals such as calcite and dolomite. You have things that are oxides, hematite, magnetite, chromite, sulfide materials. These are really pretty, pyrite, galena. This picture of galena just doesn't do it justice. It's one of the most beautiful rocks out there, and it's just lead sulfide. Pyrite is iron sulfide. So I just view the sulfide as something that makes beautiful rocks. Then you have sulfates, gypsum, and anhydrate. So I think there's a gypsum. Here's an example of gypsum. It looks a lot like calcite or like quartz. Halide minerals, fluorite being an example, and then native elements like gold, iron. So that's the small 8% remaining. So when we're classifying rocks and minerals, we start with minerals. Minerals are naturally occurring OCCURRING crystalline solids. I still can't read my occurrence, so I'm going to write it again. And then we break those down into roughly 92% silicates and 8% non-silicates. And of the silicates, if they have iron or magnesium, then they're ferromagnesium, and there's a couple examples. If they don't have iron and magnesium, then they're non-ferromagnesium. There's a couple other examples. And those, here again, we have two types of feldspars, plagioclase and orthoclase. Orthoclase, potassium feldspar, and plagioclase, sodium calcium feldspar. Now, what if it's a non-silicate? We have the carbonates like calcite, or the sulfates like gypsum, or the oxides like magnetite or corundum, or excuse me, yeah, it is corundum. And the sulfides like the beautiful galena. The phosphates, don't have an example here. The halides like halite, and fluoride is fluoride. And elemental things like gold. So now a question for you. The silicates are the most common and abundant mineral group because silicon and oxygen are. Now this is one that you don't have a reason to know why, except for, well, they are the most abundant elements in the Earth's crust. They're definitely not the hardest elements. What's the hardest thing? Diamond, which is carbon. But it's a special carbon because you could have had graphite, which is not nearly so hard. Found in the mineral quartz. Well, it is true that quartz is pure silicon dioxide. That's what quartz is, but that doesn't give us any reason for it to be the most common and formed in a tetrahedral structure. That's also true, but it's not why they're the most common and abundant mineral group. It's because they're the most abundant elements. Now, how do minerals form? Crystallization can either occur by freezing, by have molten rock that freezes. If it freezes slowly, then you have lots of crystal growth. So slow freeze gives you big crystals. By the way, scientists get very lazy and they put X tolls. You're only replacing 4 letters with that X. It's not big, but if you have a quick freeze, you don't have time to organize and you have little to no crystals. So you might, for instance, have seen when I was a kid, we'd go out and we'd look for these obsidian arrowheads. They were Indian arrowheads that we would find in campgrounds we went to. Obsidian is rock that froze so quickly that it didn't form any crystals. And in that case, it's glassy. It has no fracture, or excuse me, no cleavage. It just fractures if you break it. And it's because you don't have any crystals that formed. The other way you can form crystals is water solutions precipitating something out. So if I have water that contains calcium and carbonate, then the calcium and carbonate can combine to form a calcium carbonate molecule that then falls out, precipitates out, and starts to form a calcium carbonate crystal that would be calcite. This here is really important, something you're going to use in your homework. Minerals crystallize systematically based on the respective melting points. So I have a chunk of molten magma. So here's my chunk of molten magma. And that magma contains a bunch of elements. It contains silicon and oxygen and potassium and calcium and so on. And as it cools, the things with the highest melting point are going to be the things that freeze first. So what freezes first? Things with the highest melting point, and that means the lowest amount of silica. So things with a small amount of silicon dioxide are going to freeze first. Silica, pure silica, it has a very low melting temperature compared to other things, and so it will freeze last, and thus quartz, which is pure silica, is going to be the last thing to freeze if you are slowly freezing this molten rock. So this diagram is saying that if you have a low silicon content, then it's going to have a high melting temperature. It's going to be the last thing to melt or the first thing to crystallize. If you have a high silicon content, then it's going to have a low melting temperature and be, I don't know why that says M. I didn't even notice that. Should have been first. The first thing to melt and the last thing to freeze. You form the precipitate when you reach saturation. From the chemistry level or section, we learned that saturation is when you have more of the solute than you can dissolve. So as the water solution becomes saturated, for instance, if you have evaporation, the amount of water decreases, so the concentration goes up until you reach the saturation level, and then you have minerals precipitate out. And one of the things that's really cool is you have a rock, and oftentimes you'll see a rock that has a dike in it that's filled with a different type of rock. And that dike was filled by probably water flowing through a crack and slowly depositing rock in the crack until it filled it in. Evaporates, I've talked about that enough. Low solubility minerals they're not very soluble, so they will precipitate first. So if I have water that has different types of minerals in it, the things with low solubility will precipitate first, form rock first, and then things that have a higher solubility will be later to precipitate. A whole lot of rocks today, right? We're just studying rocks for the most part. And rocks, we've talked about silicates versus non-silicates. We've talked about ferromagnesian versus non-ferromagnesian. We've talked about how we differentiate them based on density and streak and hardness and cleavage or fracture. We also break rocks into 3 fundamental categories. So these are fundamental. And these categories are not based on what they look like, what their chemical composition is. They're based on exclusively how they were formed. Igneous rocks formed from fire. Igneous rocks were melted and then they froze. Sedimentary rocks are rocks that form from sediment, of course. That is, you had a bunch of little pieces of rock, and how did they form? Well, weathering and erosion. Weathering is breaking down a rock. Erosion is transporting it. So if I have a rock here, and I have Jim Bob who walks on that rock, so here's Jim Bob's foot. Jim Bob's foot breaks off a little piece of that rock, so that's weathering. And then wind or water makes that little piece of rock move, that's erosion. And so that rock ends up here, and then I have a bunch of other pieces of rock that end up the same place through the same process, and then they get compressed, and over time they lithify, they become a rock. So that's what sedimentary rock is. Final type of rock, metamorphic rock. Metamorphic rock could start as igneous or sedimentary, but it's been transformed. So metamorphic is transformed by heat, pressure, or chemical fluids. The typical case is heat and pressure. So you might have a calcite rock. If that calcite rock is put under extreme pressure with some heat, it will start to ooze a bit and form a rock that looks different, what we call marble. So marble, calcite, same thing chemically. The difference is that the calcite, which is a sedimentary rock, it did not come from fire. The calcite has been metamorphized to make the marble. So let's talk a little about igneous rocks. They're formed from the cooling and crystallization of magma or lava. What's the difference in magma and lava? Inside the earth, it's magma. Once it reaches the surface, it's lava. So igneous rocks, you have magma that comes to the surface. And of those igneous rocks, we have 2 fundamental types. There's so many types of rocks, aren't there? We have 2 fundamental types. We have, well, I say 2 fundamental types. There's a complete range. But if they freeze quickly, then they look very different than if they freeze slowly. And we've already talked about why. If they freeze slowly, you have lots of time for crystals to grow. And so if you look at granite, I'm just going to come up here. Granite, if you look at granite, you actually will see there's a crystal of calcite. And next to it, there's going to be a crystal of, let's say, hornblende. And then there's going to be a crystal of silicate, or quartz. And you can see those individual crystals. They're big enough, they might be a millimeter or even larger. There's going to be plagioclase. There's all these different crystals that you can see. There's this one and there's this one. They're completely separated. How does that happen? That happens if you have a very slow freezing. As far as we understand, To achieve that very slow freezing, you have to have, here's the surface of the earth, and underneath the surface of the earth, deep down, you have a magma chamber. And just like other things, when you heat the magma, when you heat it and melt it, it expands. So this magma chamber is less dense than the rock around it. Well, less dense things float up. So over time, very, very slowly, this magma chamber floats up. And the temperature outside this magma chamber is going to be cooler. And so it starts to freeze along the edges. And as time passes, it freezes more and more until eventually the whole thing is frozen. And that frozen rock erupts through the surface and it forms something like Half Dome. Half Dome is a big granitic pluton that formed from a magma chamber that froze. And so that's how we believe magma occurs. So it takes very, very long for that to freeze. So, well, we'll talk about this later, but you can't have quick grow granite because it takes time to form those crystals. But what if you have magma that comes out of the ocean floor? Comes out of the ocean floor and hits that water, it's going to freeze quickly. And if it freezes quickly, then you don't have time to grow those. So if it freezes quickly, so quick freeze, then you form things like basalt and obsidian. You don't see crystals in the basalt. It has really tiny crystals, so it feels like sandpaper, but they're not big enough for you to actually see with your naked eye like they are with granite. And obsidian, it doesn't actually have the crystals, it flows so quickly. So the difference in granite, basalt, obsidian is primarily how quickly it froze. Now, if you go down in the earth, the temperature increases at an average of 30 degrees Celsius per kilometer. So the deeper you dig, the hotter it's going to get. You might wonder, well, why is it hot down there? A few reasons. Reason number one is we have radioactive elements like uranium in the core of the earth, and they decay. Radioactive means an unstable nucleus, decays into a more stable form, giving off energy. And that energy heats up the core. So that's one thing. Another thing is, according to the scientific model, the earth formed from a whole bunch of atoms being pulled together by gravity and compressed by gravity. And that process of compressing the rocks causes them to heat up. You're pushing them on them. And so you have still cooling from the heat of formation, as we call it. And finally, another third one, which for the Earth isn't a huge factor, I don't think, but is really huge for Io, and that is the tidal forces of the sun and the moon actually cause the Earth to squish a little bit. And that squishing a little bit, just like if you take a piece of wire and you bend it, it gets hot, that also causes some heating of the Earth. Those mechanisms I talked about compose less than 1% of the Earth's total energy budget. The other more than 99% of the Earth's energy budget comes from the sun. So rocks in the mantle are near their melting temperature. It doesn't take much to make them flow. I actually talked about some important things here already, igneous rocks and the generation of magma. If you reduce the pressure, then it's going to lower the melting temperature of the rock. So if it's hot and you reduce the melting temperature by lowering the pressure, it will melt. And so pressure can cause melting or inhibit melting. I'm going to skip the analogies. If you have water in a rock, it actually makes it melt at a lower temperature. Now, it's not spraying water over the top of the rock. It's having water within it. And that's kind of similar to if you put salt in water, then it will melt at a lower temperature, right? So it's the same idea. The impurity actually affects the melting temperature. Um, so this is an important point, and it has to do with why the core is solid. Even though the temperature at depth is hotter, that is, the deeper you go in the earth, the hotter the temperature is, the very center of the earth, where it's the hottest, is solid. Why? And so is it because of the enormous pressure there? Um, well, all of these are just true. They, this is kind of an awkward, clumsy question. They're under enormous pressure, true. And that enormous pressure is what prevents their melting, true. And if you raise the temperature even higher, you probably could still melt it, true. So all of the above. I feel like I've talked about all of this already. When you have melting rock, things with a high silica content are going to have a low melting temperature. So they're going to be the first things to melt. And then as it gets hotter and hotter, you'll have the things that are less percentage silica that also melt. And so if you take something and you partially melt it, then you will have what melted is silica, and then you refreeze that and it's silica enriched. Um, well, actually, you don't even have to refreeze. You partial melt, and what melts first is silica, so it's enriched. This is saying the same thing. And yes, I did want to get to this before I ended the lecture. The mineral makeup of igneous rock is dependent on the chemical composition of the magma. That is, if you have something that is a large amount of iron, well, of course, you're going to have iron in it. And so basaltic, now remember I talked about basaltic as freezing quicker, but basalts are about 50% silica, granite about 70% silica, andesite about 60%. So these are ranges of silica in rocks. About 80% of our igneous rocks are basaltic. Granite is a small component. Granite, very slow freezing. I described this already. Rocks that form from magma that crystallize at depth, they cool very slowly. We call them plutonic, they form plutons, or we could call them intrusive. They cool slowly and form big crystals. Rocks formed from lava at the surface, they're extrusive. Intrusive, they form inside the earth. Extrusive, they form outside the earth. Or volcanic rocks, they cool quickly, and so they have small crystals like obsidian, which has no crystals. And we will stop with this talking about types of volcanoes. There are two fundamental types of volcanoes. The shield volcano, named the shield volcano because the shape is kind of flattish, or the cinder cone. Cinder cones are the ones that have the sharp sides. The difference so of course, everything has a certain composite amount to it. Composite is some of one, some of the other. But your traditional volcano that has a very exciting eruption is going to form a cinder cone because stuff comes up and then it comes down, and a lot more stuff comes down close that comes down far, and so that's how it forms the cinder cone. So the cinder cone is a sign of violent eruptions, which occurs when we have a magma that can get kind of stiff, hard, and so you have to build up a large pressure before it can erupt. So it's actually the composition of the magma that determines how it's going to erupt, that determines what it looks like. Shield volcanoes are low energy eruptions. Because the magma just flows. And a good example of a shield volcano is the Hawaiian Islands. The Hawaiian Islands are the result of a, a hot spot where you have a hole in the crust where magma from the mantle comes up and just flows out and oozes. So you might remember a couple of years ago, they had a volcanic eruption on Hawaii, and you just see this magma flowing down, going across the road, just going through people's houses and burning as it goes, and it forms this nice flat shield shape. So we'll pick up here next lecture. Have a great day.